Make sure that you take the exam before Thursday at midnight. Other than that, I guess I don't know that there's any other comments that need to be made about the exam or about what we need to do to prepare. So let's start talking about Chapter 18. In Chapter 18, we start off talking about a very familiar subject, very familiar present, very familiar, what was I going to say? Premise, and that is equilibrium, all right? Talking about equilibrium for reactions that are a little bit different, okay? They're called solubility reactions, all right? And it's appropriate that we kind of review solubility. I don't know if you've kind of noticed, but in this class, we've kind of gone over the same principles that we went over in 105, but a little more in depth, and taught a little bit more about. I got some hair sticking up. I gotta make it lay down. It's still not laying down. There we go. A little better. So this premise is about the solubility rules. All right, solubility rules. Now, solubility rules weren't exactly the funnest thing. Let me grab a periodic table here. Remember the solubility rules, and I haven't tried to grind this into your heads and have you memorize it, because you just look on Google and find a sheet, a table of solubility rules, and you can always kind of learn and remember the solubility rules. They essentially are telling us which ionic compounds are soluble when you put them into water. All right? And the rules here and what you've been taught basically kind of lead you to believe that some compounds are soluble, they do dissolve in water, and some don't. And that's the way we used to think about strong acids. There were some strong acids, and then the rest were not, right? But now, using K to help us know about the equilibrium of a given weak acid, we can now tease out the strongest of the weak acids and how weak that weak acid actually is. Well, the same is true with solubility. Again, this old chart essentially says these are soluble, these are not soluble. But in reality, there's different degrees of solubility, which, just like weak acids we can tell how weak or how strong it is by the K, because the K for a weak acid is essentially telling us how much of the materials go toward product. Well, there are Ks for solubility products. And so essentially, this K tells us how much of our material goes to solubility. Okay? So we think of a compound like silver chloride. If we remember our solubility rules, we could look at them if we don't. But silver chloride isn't soluble on our solubility rules. Chlorides are generally soluble, but with silver, not soluble. But there's a K associated with this process. So here we have silver chloride. All right, silver chloride, it's solid, and we're saying that, yes, it's not soluble, what we would refer to as soluble. However, there is an amount of this solubility that's occurring. When these separate, they find each other really fast and go back, but there is an equilibrium, so there is some concentration of this. And we can express this numerically, quantitatively, with a K. And the K here for this reaction, like it says in the slide, is 1.8 times 10 to the minus 10. All right? And this specific K is called a KSP. Now, don't be scared about those letters underneath the K. Ka, Kb, KSP, right? It's just a kind of K. And the SP stands for solubility product. Either way, it's always measuring how much the material at the left goes towards the products at the right in a given chemical reaction. All right? And just like the previous case, every reaction, or every K, is specific to a given reaction. In fact, at different temperatures, the same reaction will have a different K even, right? So, this KSP, 1.8 times 10 to the minus 10, equals, all right, who's going to help me here? Brielle, you think you can help me out? What does this K equal to? If this is K for this reaction, what is the reaction quotient?
Is it the concentration of silver and chloride?
That's right. The concentration of silver ion times the concentration of chloride ion. We don't put that over this material here. Why not, Brielle?
Because it's solid.
Because it's solid. That's right. Very good. So, KSP is a K for a reaction where generally you have a solid. So it's just going to be the reactants or the products concentrations generally. Okay? Now we still have to remember that these would be raised to whatever coefficients would be in front there. And that happens in a lot of different solubility product problems because solubility, or the lack thereof, the insolubility of the material is often associated with the fact that there's multiple charges here. Okay. So, let's write the solubility expression for silver carbonate here. All right. If I have silver carbonate, and if this were the question right there, you would know, oh, silver carbonate is not soluble. And the way that we would know that is because, well, I guess it doesn't say right here, but if they ask you to write the KSP for this reaction, you would know that silver carbonate is generally not soluble because they're asking you to write a KSP. But essentially what we do is we write our compound that they're providing there. Now, if we look at our solubility rules here for carbonate, where are we at for carbonate? There it is. All salts containing phosphate, carbonate, sulfite, and sulfide are insoluble, except those from group 1A and ammonium. So, insoluble, solid, okay? Now, if this is solid, then, there's the problem. If this is solid, we would generally think of it as insoluble, but now we're realizing that how insoluble is the question, right? Okay, so let's see, Sarah. Can you help me write the products for this reaction if we're going to show this thing being ionized?
Right, so I think it would be 2Ag plus CO3.
CO3 with a 2 minus charge, right? Whoops. And these are aqueous here. So, in the mass action expression, it would be, want to finish this up for us, Sarah? What would the mass action expression be? K for this reaction would be equal to what in terms of these concentrations?
The concentration of...
Silver ion?
Yes. Do you need to put the 2 on that? Just wondering.
You do. You need to put it up there, though, right?
Oh, right.
Squared. Then times what?
And times CO3.
CO3 2 minus to the first. All right. Very good. Excellent. So, how about this one here? Ammonium sulfate. Brielle, you want to take a stab at this one? What would do you want to write out the equation, or do you think you can do it without writing out the equation?
I will probably just write out the equation.
Okay.
Why not?
Yeah, sure.
So I'm going to the NH4 would be 2 NH4
Okay, sorry. Yep, that's right. 2 NH4s.
plus, and then added to the SO4 minus. But I mean, I guess
SO4.
it would be 2 minus. Yeah.
2 minus. Very good. So then our K for this reaction would be?
The concentration of the NH4 plus to the second times SO4 2 minus.
Very good. Excellent. And is that it?
I'm trying to look at the solubility rules to make sure that it can.
Yeah, you know, this is an interesting problem. I'm not sure because ammonium sulfate should be insoluble. Or, sorry, should be soluble. I don't know. I think that something got mixed up in this slide, but we'll just take it for what it's trying to give us for now. Another thing about these solubility rules is, again, even the ones that say they are soluble, so, you know, this group up here is generally ones that are soluble, the degree of solubility is not always complete, right? So just because it says it's soluble up here, there will always be, even for something that's completely soluble, like sodium chloride, there will always be a solubility limit, right? So solubility equilibrium expression could always be significant, even if it has a high solubility. Okay, so generally, what we want to find out when we're dealing with KSPs is what we call the molar solubility. We want to know what's the molar concentration of a given ion, or the molar concentration of the material that actually dissolves. Okay, so for this example here, when we're looking at silver chloride dissolving into silver ion and chloride ion, and we're asked what the molar solubility is, what we want to know is how many moles of this silver chloride that is put into water, because it's solid, right, actually separates, ionizes, right, separates into its ions. And so essentially, we can think of that as quantifying the moles of silver ion, or quantifying the moles of chloride ion, because for every mole of silver ion, that means a mole of this dissociated. Every mole of chloride ion, same thing, moles of this associated. And the concentration of the silver and the chloride ion will be the same in this case. Okay? So the way we would do this, we have a KSP down here, 1.8 times 10 to the minus 10. We could do this sort of thing, ice table. We could think about it as an ice table if we wanted to. But in general, the concentration of the silver ion times the concentration of the chloride ion will equal to the equilibrium constant. And so we can just say x squared equals 1.8 times 10 to the minus 10. So in this case, you know, you can write an ice table, but the helpfulness of the ice table kind of decreases. One reason why the ice table, we want to include it, is because the coefficients play a more significant role here. Again, it's because generally solubility is dealing with salts that have multiple ions per mole of the compound. So we kind of keep the ice table here so that we can, you know, clearly see what's going to be placed into this final equation here. All right, so then we're going to take the square root of 1.8 times 10 to the minus 10, and then that is going to be our molar concentration of the silver ion. It's also our molar concentration of the chloride ion, and it's the molar solubility of the silver chloride. Okay, so let's do the same thing here with the molar solubility of calcium phosphate. All right. Here, the ice table will become kind of a little more helpful in reminding us, and again, the big thing that it's reminding us is that when this solubility occurs, the concentration of calcium here, because of the coefficient, is going to be 3x. and the concentration of the phosphate ion is going to be 2x. So, if I want to write the equilibrium expression for this reaction, right, K is going to equal the concentration of calcium ion cubed, everybody okay with why I put the cube there, right? Because there's the 3 here, times the concentration of the phosphate ion squared, right? So that's my equilibrium statement. And again, this is the concentration of calcium at equilibrium. This is the concentration of phosphate at equilibrium. And the concentration of calcium at equilibrium is represented by our ice table as 3x. So this is 3x cubed, whereas phosphate here is 2x squared, and that will equal our K, which is 2.0 times 10 to the minus 29. Solving for x then will give us our concentration of the, if you look here, the x will be the molar solubility, but it won't be the concentration of the calcium. The concentration of calcium will be 3 of the x's. And the x, again, won't be the concentration of the phosphate ion. 2 of the x's will be the concentration of the phosphate ion. But the x will be the moles of calcium phosphate that actually are soluble. So the x that we solve for here will still be the molar solubility. Okay? Now pay close attention here, because what do I got? 3x cubed, is not 3x cubed is not 9x cubed, right? Obviously. So we have to think of 3 times 3 times 3. That's 27x cubed. 2x squared, that is 4x squared. Oops, I forgot the 27 there. There it is, the 27x cubed, 4x squared, equals our 2.0 times 10 to the minus 29. 27 times 4, 108. X, what happens when I multiply x cubed times x squared? It's x to the 5th. X to the 5th. So 108x to the 5th equals 2.0 times 10 to the minus 29. So make sure we can remember how to do this in our calculator. Okay. So 2.0 times 10 to the minus 29 divided by 108. Right, we're going to get the x cubed all by itself. And then we need to take the 5th root. All right. Now there's a couple ways to do this, and I'll let you look into the other ways, and I'm just going to show you this way for now. Okay, let me turn the light away just for a second so I can get a little more contrast with our calculator. I take this value and I raise it to the 1 divided by 5 power. Raise it to the 1/5 power is the same as taking the 5th root of the number. So 7.14 times 10 to the minus 7. Okay? So, again, 3x cubed times 2x squared was equal to our KSP. And then once we solve for x, 7.1 times 10 to the minus 7. So a little bit of, not terribly tricky math, but just a little bit of a reminder of recognizing that when this 3x, which is the concentration of the calcium ion, goes in here, it still needs to be cubed. And when this 2x goes in here, it still needs to be squared. Okay, so let's see if you guys got it. All right, why don't you guys take a shot at this one, try to find out what the molar solubility is. That's what x would be. Solve for x and find the molar solubility for barium phosphate. Molar solubility for barium phosphate. Okay. So hopefully while you're giving it a shot, After you're done in a little bit, Camille will tell us if she recognizes how to approach this problem at all. And if she doesn't, that's okay. Okay, Camille, how would you approach this one? Any ideas?
Oh boy. Okay. So we have to start by writing the equation, right?
Yeah, sure.
Okay. So that's 3 PO42. So would it be 3 barium
Yep.
and then PO42 minus 3?
Like that? Am I missing
Yes.
something?
There's supposed to be a 2 underneath the...
Oh, right here?
Yes?
Yeah, 2 phosphates.
Yes, right there.
2 phosphates. Okay, very good. Now what? What's next?
I don't...
Well, if we did use an ice table, what that ice table would do for us, it might, help us, especially in the beginning, to kind of clarify exactly what we're looking for here. But I'm wondering, that's, this question is asking, how much of this material will actually be converted into the ions, right? Based on that K, and the K for this reaction is a KSP, meaning that it's for a material being solubilized, 1.3 times 10 to the minus 29. Okay, so if I thought of this as my initial concentration, well, it really doesn't matter for this one, right, because it's solid. But this one, we can start off as 0. And then what would the changes be here, Camille?
Minus 3... Oh, wait, no. 3x.
Uh-huh. Plus 3x, right?
Yes, and then plus 2x.
Plus 2x. And then the equilibrium concentration would then just be what?
3x.
Uh-huh. 3x and 2x. Now what do I do? What is the K equal to in terms of our equilibrium expression, in terms of our ion concentrations?
Oh, I should have wrote that down. It's like there's... I don't know.
Well, you can just look at this reaction here, right? And we want to know what the K will equal in terms of the concentrations of these products.
Okay, so is it... I don't know.
It's the concentration of the barium, right?
So 3.
Barium squared, sorry, not squared, but barium with a 2 plus charge, raised to
The third power.
the third power, yeah. Times what?
PO4
Mm-hmm.
to the squared.
Squared. Very good. Now we just need to put in to this expression the concentration of barium at equilibrium and the concentration of phosphate at equilibrium as defined by our ice table, right? So what's the concentration of barium at equilibrium?
3.
3
Oh, wait, no.
X, right? But I can't forget to cube it, can I?
No, so that would be 9x.
Well,
Oh, no.
let's just leave it at 3x cubed for a second here, and then what goes over here?
2x squared.
Very good, 2x squared. Now, what is 3x cubed times 2x squared? Well, I should say not 3x cubed, right? This is 3x cubed like that, and this is 2x squared. So we have to take care of those exponents first. So 3x times 3x times 3x, right? What is that equal to? That's the same as, yeah, 3 times 3 times 3 times x times x times x, right? So that's 27x cubed. Very good. And this one here?
4x cubed.
4x squared, right? Very good. And now if I multiply those together with the parentheses there, then I get, what? Is that 108 again?
Yes.
X to the 5th. All right. And what does that equal? It's that, right?
1.3.
Yeah.
1.3 times -29.
Very good. Okay. Do you know how to do that math in your computer? In your calculator?
I have my calculator right here, but my calculator is different than yours. It's
Okay.
like a newer version, so I haven't figured it out yet.
All right. Okay. Well, you'll have to go into YouTube and say, how do I take the 5th root of something?
I will.
And, you know, like, there's a couple ways to do it, so I'm sure it'll be out there somewhere. But I would go 1.3 times 10 to the minus 29. I hate doing that because I don't always trust my order of operations, so I push enter there, and then I divide by 108. And then I take the cube root by raising that answer to 1 over 5. So 6.5 times 10 to the minus 7. Is that one of my answers? It is. Okay. Excellent. Any questions? Now would be the good time to ask. Okay. We can also identify, well, let's see. We can identify the KSP if we're given the solubility of the concentrations, right? So, let's see. The solubility of a salt, 80, is found to be 3 times 10 to the minus 5. What's the value of KSP? I'm just going to run through this one kind of quick, but A2, B3, dissociating would be 2A and 3B. All right? Dissociated, right? We don't know the charges, but it doesn't really matter too much. It does matter that the concentration of A squared and the concentration of B to the cube, their product will equal whatever our KSP is. Whoops, concentration not of A, of 2A and of 3B. Okay? Now, if you can't remember why is it 2A, well, think of your ice table and recognize that at equilibrium, the concentration of A is going to be 2x. So 2x squared, 3x cubed. All right? So in this case, we have 2x squared, 3x cubed, and we're told that x is 3 times 10 to the minus 5 times 2, and then that whole quantity squared, 3 times 3 times 10 to the minus 5. And again, the way we knew that is that 3 there, or sorry, that 3 times 10 to the minus 5, that x is the molar solubility. And the molar solubility was given to us. Okay, so that would equal our KSP. So we could put that into our calculator and get our KSP. Okay. All right. Now, when a compound like silver chloride dissolves in water, and again, we know it's sparingly soluble, that's what we say, right? It's not soluble, but there is a K, and so there's a little bit of solubility, right? When a compound like silver chloride dissolves sparingly, there's a K associated with it, so we can tell people exactly how much it will dissolve, how much will be around, which is a big deal, right? Because if you have lead pipes, for example, And there's still lead pipes used in the world today. The lead pipes can get oxidized on the inside and create lead oxide. Now, people used to say, that's not a big deal, lead oxide, that's all right. But because lead oxide is a solid, just like the lead was a solid. But lead oxide has a degree of solubility, right? Has a degree of solubility, and that lead oxide will ionize to a degree, releasing lead ions, and the lead ions can be poisonous, right? You've heard about different counties I don't know if you paid much attention to them because maybe wasn't you, didn't matter in your life, but some counties don't have the chemical understanding necessary to prevent the water system that they have from releasing poisonous ions into solution, into the water system. And sometimes they'll make changes to how their water system works by maybe washing the pipes or using different additives in their water supply to kill bacteria or compensate for too much chlorine or whatever. But if those additives change the solubility, and we'll see how you can influence the solubility of these salts, then the concentration of lead or whatever heavy metal ions can be changed in your water supply as well and cause serious problems, right? So, one way that solubility is influenced is through what we call the common ion effect. This KSP here will tell me how much a silver ion and how much chloride ion I can expect if I have solid silver chloride in solution. However, if I try to dissolve this silver chloride, and let me draw a picture to make sure we understand what's going on. Here's my container of water. Here's my pile of silver chloride on the bottom, right? It's just a solid, so it's not dissolving a lot, just a little bit. But if I also try to put a little bit of sodium chloride in the solution itself, the solution itself has some soluble chloride ion in it already, then when I write out my ice table, the concentration of chloride ion will start here at some value. Maybe I put in 0.2 molar sodium chloride, for example. And that concentration of chloride ion, when the KSP is actually written, silver ion concentration, chloride ion concentration, right? The change, you'd still get plus X, right? But the equilibrium concentration would be X, and this would be 0.2 plus X, okay? And because of that 0.2 plus X, that concentration of chloride ion is going to alter the amount of silver chloride that will actually dissolve, okay? So this is a way to keep silver or heavy metal ions in solution by increasing the salt concentration in the water itself, okay? So here's an example. What's the molar solubility of calcium phosphate? Now we just kind of did this one in 0.1 molar sodium phosphate, okay? In 0.1 molar sodium phosphate, well, the calcium phosphate dissociation is going to be influenced by something in the sodium phosphate. Okay? Now, to determine what it's going to be influenced by, we can write the solubility expression for calcium phosphate. Ca3PO4, supposed to be dissolving into 3 calcium ions, and 2 phosphate ions. Okay, that's what's going on here. And we want to know the final amount, the molar solubility that actually dissolves if we start off with 0.1 molar sodium phosphate into solution. Well, the 0.1 molar sodium phosphate, is that going to influence how these ions interact with each other, or how this salt dissociates? What do you think, Brielle? Which one of these ions, or will either of these ions influence how this salt wants to dissolve?
The PO4.
Okay, that's right, the phosphate. Because it's one of the products, and like Le Chatelier's principle said, and we've kind of already mentioned, that if you add a product, it will shift the equilibrium towards the reactant's side. So initial concentration, this one we don't care about, it's solid. But the calcium ion concentration starts off at 0, and the phosphate ion concentration starts off at 0.1, because if I put 0.1 molar calcium phosphate, or sodium phosphate, into solution, I end up with 0.1 molar phosphate ion. The change. Now there's still no calcium. There's still no calcium. So our Q is still going to have 0 on the top. Therefore, not 0 on the top, 0 as the expression, right? It's going to be the concentration of this 3 times the x, 3 times x cubed, right? But if 3x is still 0, then we're still going to need to shift to the right. So we still know that this is a positive x, and positive 3x, because the 3 there, and a positive 2x there. So now this concentration is 3x plus the 0, and this is 0.1 plus the 2x. These are my equilibrium concentrations for those ions. So I need to take those values and put them into the equilibrium expression. The equilibrium expression is the calcium ion concentration cubed and the phosphate ion concentration, PO4 3- squared. So this is my equilibrium concentration for the phosphate ion, 0.1 plus 2x, 0.1 plus 2x squared, and this is my calcium ion concentration, 3x cubed. Okay, and that is going to equal 2 times 10 to the minus 29. So if I can solve for x, it will tell me the equilibrium molar solubility, molar solubility. Now, this begins to look messy, and so we think about this shift, which is this change, this shift of dissociation, the 2x there. If I take 0.1 and add 2x, is there any way that I can drop that 2x? I'd like to drop the 2x because I can see it's getting messy in here. It's going to have a quadratic, but I'm going to have to multiply by that. Put that into, that's going to be more than just a second order polynomial. So I'm not going to be able to, if I could use my, couldn't use my quadratic equation. I could still use my solver, but anyways, it's going to push us over our limit of desirability. We're not going to want to work on that. So we say, what can we do? What do you think, Sarah? Do you think I can drop that 2x?
I would think maybe you can, because KSP is super small.
That's right. That's what we look at, right? Because this is 0.2 or 29 zeros, right? And this is only 1 decimal place moved. We're way, way, way far away from each other. So this shift is not going to influence that 0.1. Thank goodness, right? So I can simplify this to 0.1 squared times 3x cubed. This is 27x cubed. I know because we've done that a lot, right? 0.1 times 0.1 is 0.01. Okay. This equals 2 times 10 to the minus 29. And then we can just solve that in our calculator. It doesn't matter if I multiply this through or divide it individually. So 2 times 10 to the minus 29. I'm just going to divide it by 0.01, and then I'll divide it by the 27, and then I want to take the cube root of it, so to the 1 over 3 power, so x is 4.2 times 10 to the minus 10. All right, 4.2 times 10 to the minus 10, right? And that would tell me the concentration of the calcium phosphate that would dissolve. How would I find the concentration of phosphate? Now, phosphate is not something that you want to have a lot of. There's an upper limit, a higher limit than something like lead or silver or mercury in your water, but you don't want to have a lot of phosphate either, right? What if this was my X now, which is my molar solubility, how would I find the concentration of phosphate? What do you think, Sarah? Would that be the concentration of phosphate? What would that be?
So that's just X, and we said the phosphate total is 0.1 plus 2X.
Very good. Very good.
So, yeah.
So we can take the X here,
That number, right?
multiply by 2, add 0.1, and that'll be our concentration. And for the calcium concentration, this value times 3 would be our concentration of calcium. Excellent. All right. So, did we get 4.2 times 10 to the minus 10? Yes, we did. All right. Awesome. Let's let you guys give this one a shot. And look, it's Camille's turn again. She always is the lucky one. She gets to do the new problem.
I don't understand why I'm not so lucky. Okay.
All right. So, how would we approach this, Camille? What would we do?
Okay. Well, first we need to make a table.
Okay.
Not necessarily first. First you can do the equation.
All right. So we got barium sulfate. What are the products going to be?
That's it.
Just
Barium sulfate.
it's barium sulfate is the reactant, and barium with a +2 charge, right?
+2, and then SO4 has a -2 charge.
Yeah. Now I don't know if any of you guys have ever gone to the hospital for abdominal pain, right? I think still pretty much the treatment, it's been for many years, not the treatment, but the way to detect the problem with abdominal pain, abdomen, pain in the abdomen, right? In your digestive system somewhere. If you have pain and you go to the doctor, they're going to say, after a variety of tests and they can't figure out what's going on, then what they'll do is they'll do a kind of a CAT scan on you after you drink a given milkshake, right? It kind of tastes, they try to make it taste decent. It's really chalky. You drink it, and they put you in kind of a radioactive machine that can detect the presence of what you've just drinking, and then watch how it goes through your digestive system and see if there's leaks or clogs where there shouldn't be, right? And what it is that they give you is what they call a barium shake. It's a barium shake. Now, barium is very toxic to us and it can kill us. However, they're relying on the insolubility of this barium sulfate in solution, okay? So, or barium carbonate or whatever it is. So they have to make sure that the amount of barium ion that actually will be soluble will not be enough to kill somebody. And that's pretty low concentration, or poison somebody, and that's pretty low concentration. So this kind of exercise here would be critical in developing any sort of detective shake that people might be taking to solve problems with their pain in their digestive system anywhere. Okay? So we need to know how much barium ion will actually be in solution to prove to the FDA, for example, that this is not going to be a poisonous procedure. Okay? All right. So, Camille, what's next?
The table.
Okay. What do we do?
Well, initially, there's none.
Of
Right.
what? None of what?
Barium.
Barium? Well, I think that's what kind of makes this problem a little bit different what do they say here? Calculate the molar solubility of this stuff in 0.1 molar barium chloride. So we already started with 0.1 molar barium chloride in the solution.
So would it be 0.1?
Yeah. Is my screen frozen?
Yeah.
Why is that?
I'm gonna come out and come back in.
No, I don't think it's your fault. I think I better do that.
Okay.
Okay, let me try to... Okay, can you hear me?
Yeah. I just can't see it.
You guys still there?
Yeah, I'm here.
Yeah.
Okay, so we're getting a problem with something.
Did you turn on your screen share?
Yeah, I tried and it's telling me that there's a problem. Oh, here we go.
Oh,
There we go. Okay. So our concentration of barium to start off with, initial, is actually not 0. It's 0.1.
0.1.
What's our concentration of sulfate to start with?
Will that just still be 0.1?
That will be 0. That will be 0. Because we have no sulfate, no source of sulfate here. Okay, very good. The change. What's the change?
0. They didn't add any, so it's just 0.
Well, because this is 0, we're going to have some more of this dissociate because there's none to start with, right? So there is going to be a change of positive, and these are just 1s up here. So
Okay, so it's just 1.
plus 1x, and then plus 1x. So the concentration equilibrium here, 0.1 plus x, and x. And now, how can we solve for x? How do we find out what x is? What's next, Camille?
Do you use the KSP?
Yeah. 1.1 times 10 to the minus 10. What do we set that equal to?
0.1 plus x.
0.1 plus x
Plus x.
times what?
Oh, times x.
Times x. And both of these are just raised to the 1 power, so that's nice. Okay. That's not terribly hard if we get 0.1 x plus x squared, but it's still a little uncomfortable. Is there any way we can get rid of this x here to simplify it for us, Brielle or Camille?
I don't know.
What we have to do.
I can not multiply it, but I don't think so.
What we have to do is we have to look and see how large this KSP is. Because it's so small.
So would you plug that in for x?
What did you say? Say it again?
Would you plug that in for x?
Well, you could.
Okay.
You could think of it as plugging that in for x. But when you would do that, 0.1 minus this really tiny value, it would still just be 0.1. So essentially what we're doing is kind of in a way plugging that in for x, or recognizing that that x is not going to influence 0.1. And so we just say we're dropping that x. Okay?
Okay.
So 1.1 times 10 to the minus 10 equals 0.1 times x. Multiply this by 0.1, that's 1.1 times 10 to the minus 11, and that is equal to our x So that is our molar solubility of barium sulfate. How does that compare to the concentration of barium, Camille?
Well, the concentration of barium, is it just talking about how it's 0.1? Like, is that the concentration we're looking at? 0.1 molar?
Let me back up one step right here. 1.1 times 10 to the minus 10 divided by 0.1 isn't 1.1 times 10 to the minus 11. It's 1.1 times 10 to the minus 9. Sorry. There we go. So how does this X relate to the resulting concentration of barium?
It's how much is left.
It's how much that X, in this case, in the previous problem, it was, you had to multiply it by 2 or 3 to identify the concentrations of the ions here. But in this case, the concentration of the sulfate, for example, is this value. The concentration of barium is 0.1 plus that value. So the X isn't multiplied by 2 or 3 here. It's just that is the concentration of sulfate. And that is also the molar solubility for our barium sulfate. Okay, very good. Let's see. How will the solubility of barium phosphate change if barium chloride is added to it? All right, so Sarah, you're going to try to think about this problem here for a second. Let me kind of draw a picture so we know what it's asking. I have in this solution a pile of barium phosphate. Now, I drew it as a pile because it's not soluble, right? I have a pile of barium phosphate, and this is water. But now I add some solid barium chloride into that solution. Okay? So if I add some barium chloride into that solid barium chloride into here, chloride ions are generally, or salts containing chloride ions are generally soluble. Silver and lead and mercury are exceptions. But now we're going to get barium ions and chloride ions floating around. Right? So how is that going to change how much barium phosphate is actually dissolved in solution? What do you think, Sarah?
I would think the solubility would increase.
Would decrease?
Yes.
Yeah, that's right. It decreases. Now, if we want to kind of draw that out to think about it, barium phosphate, if it's solubilizing, we're saying that barium ions and phosphate ions are in the product side. But when we add barium chloride, we're adding more barium ions, which is going to push the solubility back towards the left. All right? Push this equilibrium back towards the left. Okay. Excellent. Now we can also do a couple other tricks that I kind of want to introduce you to. We can look at the saturation, the current Q, and compare it to P, to the K, and find out whether the equilibrium is going to shift, if there's going to be a change towards the products or towards the reactant side. So, 20 milliliters of 0.1 molar calcium chloride plus 20 milliliters of 0.01 molar sodium oxalate, carboxylate. Okay, so calcium chloride is soluble and sodium carboxylate is soluble, but calcium carboxylate is not soluble. Calcium carboxylate is not soluble. So will a precipitate form? What we have to do here is know the KSP, and the KSP for calcium carboxylate is 2.3 times 10 to the minus 9, and therefore, at equilibrium, the concentration of calcium times the concentration of carboxylate, if it equals 2.3 times 10 to the minus 9, then you'll get precipitate forming, or, right, you'll get the products here going towards the reactant. Okay? So, we just have to look at what our concentrations of calcium and carboxylate are, multiply them together, and see if they equal 2.3 times 10 to the minus 9, or a value that's higher than that. Okay? So, let's find out what the concentration of calcium ion is when we mix, like it says here, 20 milliliters of 0.1 molar calcium chloride and 20 milliliters of 0.01 molar sodium carboxylate. Well, if I have 20 milliliters of 0.1 molar calcium chloride and I add it to 20 milliliters of something else, the total volume is 40 milliliters. So the concentration of my calcium chloride, it was 0.1, but now it's divided by 2 because there's twice the volume here. So the final concentration of the calcium chloride is half of that, not 0.1, but 0.05 molar calcium chloride. Right? And this is a soluble compound, so that means that I'm going to have 0.05 molar calcium ion in solution. So that 0.05 molar is my concentration of calcium ion that goes into this component right here. Carboxylate ion concentration. Brielle, can you help me with the concentration of the carboxylate at equilibrium here?
So you would take the 0.01 divided by 2?
That's right.
And be it, yeah.
0.005, right? And that is my concentration of the C2O4 2- ion. Okay, very good. So, 0.05, concentration of my calcium ion. 0.005, concentration of my carboxylate ion. I just find the product of those two. 2.5 times 10 to the minus 4. 2.5 times 10 to the minus 4. That means, and we said at equilibrium, so 2.5 times 10 to the minus 4 is now my Q, that's the current quotient. But at equilibrium, what will these concentrations equal at equilibrium, Brielle?
2.3 times 10 to the negative 9.
Okay, our KSP. So if we're currently at 2.4 times 10 to the minus 4, will this shift towards more soluble ions or towards less soluble ions?
Well, because it's bigger, will it move to the left?
That's right. It'll move to the left and it'll form this solid, this precipitate. Very good. So it will form a precipitate. Here's another example. 10 milliliters of this material, 10 milliliters of this material. We can look at these compounds, lead nitrate, calcium chloride, and think about the precipitate. Our solubility rules tell us that lead chloride will be the precipitate. And, you know, it won't be very hard for us to figure out what kind of precipitate they're looking for because they have to give us some KSP. All right. The concentration of lead ion, once I combine 10 milliliters of 0.1 molar with 10 milliliters of this stuff, is going to be not 0.1, but 0.05, half that concentration for the lead ion concentration, right? So the lead ion concentration, 0.05. The chloride ion concentration here is going to be 0.001 divided by 2, because I diluted it with this stuff. However, because there's 2 chloride ions for every mole of calcium chloride, I multiply it by 2 again. So it's going to be 0.001, just as it's written, 0.001. And that is the chloride ion concentration. But I need to, like it says here, the chloride ion concentration squared. All right? Because the equilibrium statement says that value squared. So if I take 0.001 squared times 0.05, I get 5 times 10 to the minus 8. 5 times 10 to the minus 8. That is my Q. All right? What do you think, Brielle? Well, let's see. I think Brielle just answered this question. So, Camille, your turn. If my Q is at 5 times 10 to the minus 8, will I form a precipitate? You have to look at our KSP,
I want to say
right?
yes, because it's 1.7 times 10 to the negative 5, so would it be form a precipitate?
Okay, so this should be at equilibrium 1.7 times 10 to the minus 5. Which value is larger, 1.7 times 10 to the minus 5 or 5.5 times 10 to the minus 8?
5 times 10 to the minus 8.
Is larger or smaller?
Oh, it's smaller.
It's smaller. So our quotient has not quite reached the concentrations necessary to push this back towards a precipitate. Therefore, we will not form a precipitate. Very good. I have a meeting I need to go to, so this is where our class ends today. Thank you so much for participating. If you guys have any questions, I could answer them. Otherwise, I will see you guys on